Dr. Mihir Sen steals hours from his sleep to analyze his experimental data and to plan ways to improve his experiments. He has to his credit a varied range of inventions, from a garbage recycling plant to a room temperature superconductor. He's a man with an itch for inventions. The young Mihir Sen was a rather ordinary boy. His father, Sri Obonikanto Sen, nurtured ordinary hopes of a father for his ordinary son. As an undergraduate student in chemistry at the Ashutosh College, Calcutta, Mihir Sen was more or less undistinguished, although he did show glimpses of original thinking.
When I was a student of intermediate in science, at that time one of my subject was biology, that means botany and zoology. In their World magazine, I published one paper on vitalism. At that time, I have tried to show that how life can be prepared in a laboratory in near future.
When the young Mihir Sen joined the engineering college at Leeds, England, little did he foresee that a day would come when accolades from all over the world would come pouring at his doorstep. But something happened during his years at Leeds.
Professor J.C. Moore, he was a visiting professor of our university, and also he is the director of a British Cast Iron Research Association, Birmingham. One day, we both are moving inside a cast iron foundry to see how some casting can be produced. That was a lunchtime. In the crucible, the liquid cast iron was left in the melting condition because the workers they had gone for lunch. What happened? Professor Moore, suddenly he has seen some metal in the ground near the cupola. He threw it in the liquid metal. And surprisingly it was noticed that the graphites of the cast iron that is turned into a nodule form. Then Professor Moore started saying, "Eureka, I have discovered something." Finally it was found that he has discovered the spheroidal graphite cast iron, which is known SG iron. And that is a metal which has got physical property nearly the steel, but casting and other things is like a cast iron. By seeing this one, I understand that invention is a very simple thing. So my mind then turned from an engineer to a scientist.
So, Professor Moore set Mihir on the path of inventions. For Dr. Sen, there was no turning back from this path. An additional bonus came his way when he got a chance to earn his sustenance at Leeds by making microstructures of different metals. In the year 1968, Mihir Sen read his first major paper at the Fourth World Conference on titanium. While doing his postgraduate studies at Nuremberg University in Germany, Mihir Sen developed a method of melting titanium under nitrogen atmosphere.
An attempt has been made to make a cost-effective furnace design on which nitrogen atmosphere has been carried out, and by this nitrogen atmosphere your vacuum system completely removed. This is a plasma electrode, this is a negative electrode, and this is the positive electrode. This is a ladle in which titanium sponge caved, and this is melted, and this is the casting mold. And this is the inert atmosphere.
Sen also showed that adding 2.5% hydrogen to titanium alloys yields good results.
It can be evident that similarly for ultimate tensile strength, hydrogen addition of 2.5% is giving the maximum value.
Dr. Sen has proud memories of his first presentation on such an important public platform.
So when I delivered my lecture in the Fourth World Conference on Titanium held in Munich. After the paper is over, my chairman of the dais was a Japanese and also an American. During the sum up, the Japanese chairman, he said that Dr. Mihir, he has given the findouts which is 1 decade ahead than the Germans. So this also increased my moral support very much.
Even while working abroad, Sen always had India's interests in mind. He realized that titanium is the metal of the future. It is hard, light, corrosion resistant, and heat resistant. It is ideal for making aeroplane parts, underwater pipelines, or even inserting into the human body. India has vast reserves of its ores, rutile and illuminite on her shores and beaches.
Titanium is a wonder material. It is called the material of 21st century. In India, we don't have this type of capacity to manufacture. So there's a huge scope for Indian industry to set up titanium plant for making titanium tubes, plates, and heat exchangers.
Dr. Sen thought of diverse applications of this metal. In France, at the INSA, in the year 1986, he developed an artificial heart valve using a thin wafer of specially designed titanium alloy. He even used titanium for curing AIDS. As far back as 1976, when AIDS had not yet become a worldwide epidemic, Sen designed a photodynamic therapy where a beam of protons and neutrons irradiated on a patient would kill the HIV virus. The neutrons would be emerging from a titanium alloy on being bombarded with alpha particles. The collimated neutron beam mixed with photons from a laser would act as deadly rays for the HIV virus.
The system, since it is very, very expensive, required millions of dollars. So one company, your Messrs. Technology Transfer Inc. of Baltimore, they came forward to develop this prototype equipment.
This work fetched Sen a PhD degree from Krakow, Poland. He was fortunate enough to have as his guide Madame Curie's cousin, Ludmila Lake.
Quite often, we are going to various places from Krakow by train to carry out various experiments on neutron photon and on superconductor experiments. And what happened, she brought various type of foods. So in the morning, she was giving me these foods in the train, and the passengers who were moving with us in the train, they are so much excited that how Madame Curie's cousin sister is giving foods to an Indian student.
Indeed, his peers have all been great inspiration in shaping his life. At Nuremberg, he was a student of Professor Zwicker.
Professor E. Zwicker, he was my guide in the Erlangen University. He is a very hard taskmaster, not only in the university, but also during the experiments carried out in various practical field. And quite often he was taking to his house. In his house on the top floor, he has a separate laboratory. And sometimes what happened, he was giving the work to develop the electronic field, to do some microstructure, and the whole night sometimes I am spending with him.
Today, when he works tirelessly to perfect his room temperature superconductor, he often thinks of Professor Zwicker working away at his attic for long hours. Professor Zwicker had taught him the mantra that there is no substitute for rigor and no shortcut to success. Dr. Sen's search for the superconducting material began as early as 1968 in Nuremberg while working with the alloys of titanium. he developed a niobium titanium alloy whose resistance gradually decreased with decreasing temperature, but abruptly dropped to zero at 5.7 degrees Kelvin in a liquid helium environment. The knee of this graph is called the critical temperature. Superconductivity remained an academic interest. Anything becoming a superconductor at such abysmally low temperatures was of little use to mankind. But things suddenly warmed up in the year 1987 when Professor Muller discovered that certain oxides show superconducting properties at 35 degrees Kelvin. The compound barium lanthanum copper carbon passed the test of superconductivity by demonstrating Meissner effect. New vistas opened up. Now it became easy to visualize levitated trains floating on air cushion. Sensitive human imaging through strong magnetic resonance, and, above all, transmission of electricity without any wastage became a plausible idea. Immensely powerful magnetic fields could be created by small electromagnets. All gadgets would shrink in size. Computers would become smaller and faster. A worldwide race began to push the critical temperature higher and higher. Professor Paul Chu of Texas soon attained a critical temperature of 90 degrees Kelvin. Dr. Sen too was drawn into the race. In the year 1990, he developed bismuth, strontium, calcium, copper oxide with a critical temperature of 135 degrees Kelvin. In the same year, he improved his results by 5 degrees by trying other elements. These new compounds were tested at Stanford and Colorado and also at the AT&T Bell Labs. These were confirmed to be the highest temperature superconductors achieved in the whole world. Dr. Sen was awarded the patent for his new compounds.
Regarding superconductivity, I have gotten information from one professor, Professor Kissinger, from North Carolina University. He sent me a congratulation letter that maybe the next year I'll be one of the Nobel laureate.
Unless a superconducting material is drawn into wires, it is of little practical use. So, Dr. Sen devised a method for making wires out of these ceramics by filling a powdered material inside a narrow silver tube. One such 1 meter long cable was presented to Magnetic Power Incorporated. Later, he built a transformer with such wires. Dr. Sen's main concern has been appropriate applications of superconductors in India.
Melting technology, some of which this is a practical experiment for showing how the current can be pulled in the foundry during the load shedding. Here, this is the battery, and if you can close this battery switch, then current will rotate inside. This is the superconductor loop, inside this superconductor loop. But to test whether the current is stored in the superconductor loop, you close this one and then observe through this magnetometer is there for detection. And you can find that there is no loss of current inside the loop.
The soot in this smoke always has some iron particles, so it can be attracted by a strong magnetic field of an electromagnet made out of superconductor wires.
In environment control, you can control the pollution inside the foundry by superconductor magnet. On the cupola, when your fumes are coming, you can put a small superconductor magnet which will condense your carbon particles, iron particles, and other polluted material and will come down.
At the laboratory at Calcutta, Dr. Sen has set up a prototype model for purifying bauxite and magnesite ores. These ores are rich in silica that make them poorer in quality. They crack easily when used as furnace lining. If these ores are powdered and passed over a superconductor magnet, the silica is attracted and the pure ore separates. The silica invariably has traces of iron.
But in some geological state where silica contains no trace of iron, that means silica is a paramagnetic. So it is a non-magnetic material, their silica. How to remove? Here we have used your microwave interactions. These microwave interactions will accelerate a mechanism within the silica, and it will convert your paramagnetic to diamagnetic. Then this diamagnetic silica will be removed by this superconductor magnet.
The superconductor electromagnets are immersed in liquid nitrogen. They have a magnetic field of about 2.5 Tesla. Pure ore separated this way is again pressed into bricks for use as furnace lining. But things would be so much simpler with a material having critical temperature near about the room temperature.
An attempt has been made to remove mercury with some other stable compound like your gold or silver, by which a stable TC above 170 K should be achieved in near future. And since by this bulk material and wires TC cannot be increased 180 K, therefore we are developing oxidized polypropylene. This oxidized polypropylene work has already been done by Professor W.A. Little, quarter of a century ago, and he has written a number of scientific articles in various journals like Physics Review, Physics Letter in the year 1964. On the basis of his published work and the different experiments carried out in different laboratories, and also the work we have done in our laboratory, your oxidized polypropylene has been developed.
So, it seems oxidized polypropylene was the answer to the quest for room temperature superconductor. Meissner effect for these materials are tested in a novel way. Held between two copper sheets, these vibrate between the two poles of a permanent magnet if they are repelled. Repulsion by magnets is the acid test for superconductivity. Once again, a nomination for the Nobel Prize was inevitable. Dr. Sen is still working at perfecting his inventions. Superconductors tend to lose their superconducting properties when high current passes through them. The maximum current density for which a substance remains a superconductor is called the critical current density. Critical current density for his oxide superconductor is 4 billion amps per meter square. He is attempting to raise it to 50 billion by bombarding the sample with a beam of protons. It so happened that when Dr. Sen was working with the TC and JC graphs, his grandson playfully drew the lines towards higher temperatures. To make his grandson's prophecy come true, Dr. Sen has been trying his best to raise the values of TC and JC of his samples. He has dedicated his books on superconductivity to his grandson. It is a tough job to remain ahead in the rat race, more so for someone belonging to a developing country.
I can remember that at the time the various scientific community in the United States, they said that we are spending millions of dollars for this superconductivity. Then how an Indian scientist first received the highest superconductor value of a patent from United States. Then on that basis, when I was in California University, then California University said, okay, in your next patent, we'll be your assignee. And in the next patent, also I filed in United States, and I have been granted in May 1996. And on that basis, I have also filed in Europe a patent which covers the entire Europe, all the countries.
The patent was granted only after copies of his work was sent all over the world and verified thoroughly. Although a large chunk of Dr. Sen's time is taken up by the superconductor race, he is equally concerned about the problems faced by his native city, Calcutta. Garbage disposal is a big problem in any metropolis. He has set up a garbage processing plant at Howrah. In his lab, he is working on the thermophilic bacteria whose level of activity increases at higher temperatures of about 60 degrees Celsius. These bacteria can produce methane from garbage at a 60% faster rate. He has hit upon another novel way of increasing bacterial activity in the garbage. If the garbage diluted with water is left exposed to a laser beam for a day, the bacteria gets activated.
He has put in a few decades of service to the foundry industry, and he has now developed various foundry processes, melting technology, some of which have found wide application in some key sectors.
By using a small chips of 3-inch square of a superconductor chips, you can control 1,000 computers in a foundry without any power failure. But the chip size is maximum 3-inch square.
These are the spheres of activity of the man nominated 4 times for the Nobel Prize.
In the rat race, the increased TC, a lot of millions of dollars are spending both in United States and Japan. And Japan is going ahead how to increase TC because the room temperature superconductor is the main achievements by all scientists in the various laboratories.
But how does he cope with the disappointment of not getting the coveted award?
If Nobel Prize will not come on my way, I don't mind for that. I will do and carry out my experiments as long as I will live, and will establish new theories, new results for the young generations.
Thus, for Dr. Sen, results of his experiments are important, not the rewards that may or may not follow. In the words of the Gita, Karmanye vadhikaraste ma phaleshu kadachanam.